This is the second session in our Learning from Data with Information Theory and Causal Inference. And our first speaker is going to be Elena Robiva of University of British Columbia. So take it away, Elena.
Great, thanks, Joe. So today I'll talk about how to learn linear causal models using algebraic constraints. So causal models are useful in many areas in the sciences. Here I have two examples of gene regulatory networks and disease diagnosis graphs. And I think we're all in this session familiar of the importance of causal inference. And the questions that I'll be asking is how can we learn the structure of these graphs from observational data? All right, so we'll be working in the framework of structural causal models where we have a graph, a directed graph, and each variable xi is a function of its direct causes or its parent in the graph and some noise. So here, for example, x4 is f4, some function of x1, x2, x3, and the noise epsilon4. The noise terms are independent of each other. And then in general, a structural causal model consists of directed acyclic graph, or at some point we might have cycles in a bit, G, and with vertices Z and edges E, where there's one variable xv at each vertex, and xv is the function fv of its parents, of x parents of v, and the noise epsilon v. And again, we assume that the noise terms are independent. And given samples from such a model, we would like to identify the graph G. So there's the different settings of these models. So for example, in general, if you don't assume anything about the functions, or if they're Gaussian or the variables are discrete, then there's Markov equivalence, meaning that you can't uniquely identify the graph G. You can only identify it up to Markov equivalence. So you often won't be able to say what the unique graph is. And there's other settings where you can impose something and then you actually get the unique graph. So for example, nonlinear, if the fi functions are nonlinear, but the noise is additive, or if they're linear and the noise is non-Gaussian. And today I'll talk about these linear non-Gaussian models. And so in the linear case, again, every variable is a linear function of its causes, direct causes, plus the noise. So for example, x4 here is a linear function of x1, x2, x3, and epsilon4, and the epsilons are independent. That's because we're assuming there's no unobserved confounders at the moment. And here these lambdas are the coefficients. Okay. And then again, if we have a general directed acyclic graph G, then the linear structural equation model corresponding to V consists of the graph and the variables at each vertex and the equations where xi is a sum over j going over the parents of I of lambda ji x j plus epsilon I, and the epsilons are independent. Sorry, there's people coming and I have to accept. Do the co-hosts see this thing where you have to admit people, or is it just me?
Yeah, I can see it as well, so
okay.
I can take care of it.
I forget. Okay, and so so for these linear structural equation models, you can rewrite the equation in matrix vector format. So you can write the vector x equals to lambda transpose x, where lambda is the matrix of coefficients plus the noise vector epsilon. And note that lambda is going to have zeros if there's no edge. So lambda ji will be 0. I guess is lambda trans. So lambda ij will be non-zero if there's no edge from I to j. So lambda actually contains the information of the graph and basically the whole model because it has the coefficients. And equivalently, you can place this lambda transpose x on the left, subtract it, and then multiply by I minus lambda inverse transpose both sides, and you get this equation. And here, if your graph is acyclic, then you can show that this matrix is always invertible. So you can always do this. And so, so I'm going to have this equation on the next slide. Okay, so we have a DAG, X is I minus lambda over transpose epsilon, the epsilons are independent, and lambda lies in what we call R to the E, where E are the edges of G. So lambda ij is 0 if there's no edge from I to J, and possibly non-zero otherwise. So this is sort of our model, and we have samples from this random vector X. And this is very similar to something called independent component analysis, where you have X is A epsilon, where A is some linear transformation of a matrix, and epsilon is a vector of independent components. And you want to recover A. And you can't really recover A uniquely, but all you could hope to do is recover it up to permutation and scaling of its columns. Because if you permute the columns of A, that's the same as permuting the corresponding noise terms in epsilon. And if you scale a column in A, you can rescale the corresponding epsilon term. Like if you scale the I column, you can scale epsilon I by 1 over that number. And so you won't be able to tell the scale, but after permutation and scaling of the columns, you can hope to recover A. So it turns out that if at least 2 of the epsilons are Gaussian, then recovering A uniquely is impossible. And this is also one reason why, if you have a Gaussian graphical model, you can only recover the graph up to Markov equivalence. But if all but one of the epsilons are non-Gaussian, then A can be recovered up to permutation and scaling. And there's a variety of methods for ICA, so this independent component analysis, that one can do to recover the matrix A. And so this problem, which has been studied for quite a while, becomes useful in our setting of learning linear structural equation models. So in 2006, Shimizu et al. Were sort of the first to realize that if the noise vector is non-Gaussian, then you can actually use ICA methods to estimate this matrix and therefore estimate the graph. And there's a lot of literature that follows that has a variety of methods that are proposed. So the ones that use ICA are not necessarily the best, because ICA sort of suffers from some kind of non-convexity and things like this. And also, when you get an estimate, there will be a lot of you have to threshold and choose which entries are 0 and non-zero, and you're not really exploiting the fact that there is an underlying graph. And so a lot of the methods that follow do some more combinatorial things to learn the graph. And so here I'm only citing a few, but there are many other papers. And one of the most recent ones that are also successful in higher dimensions is this algorithm of Wang and Durton in 2018, which actually exploits relationships among the second and higher moments of the vector X. And so I think this is a very nice explanation of why the non-Gaussianity works. So, so the two graphs, 1 causes 2 and 2 causes 1, are Markov equivalent. So if you're Gaussian or general, you can't actually distinguish these two from observations. But here's this one equation, it's the same one, which is 0 in the first case. And so this equation, so these are sort of second moments, here x1, x2, and x1 squared, and E of x1 cubed and E of x1 squared x2, those are third moments. So this one is 0 in the first case, always. And in the second case, it's non-zero generically, meaning for most, probably 1 if you choose the values of the lambda arising from this graph. And the noise terms, I guess, their second and third order moments should be chosen generically non-Gaussian. Then this will be non-zero. And so this gives you a way to distinguish those two graphs. And their algorithm of Wang and Durton uses this precise equation basically to learn the whole graph, because if you take one and any other vertex, so if you take a source node and any other vertex of the graph, this equation will be 0. So this allows you to identify all the source nodes, and then you can regress them, and then basically get a graph that does not contain this node, and you can regress them on them in the data, take the residuals, and then you have data that arises from this graph without the node 1. So you can continuously peel off source nodes until you are done, and then you can easily learn the weights on the edges. This is sort of how to do this. And this is similar to this direct Lingam method, but yeah. They just don't use the cumulants, they use some other independence tests. Okay, so right. And so if we just now think about all of the higher moments, we might be able to, maybe we can say something more. So the linear structure, we're going to define this object M23 of G to be the set of second and third order moments of random vector X corresponding to a specific graph G as follows. So this might look a little scary. So it's going to, so the second moments of a vector like this are what? These are the covariance matrices. And so here omega-2 is the covariance matrix of epsilon. And since you're multiplying epsilon by I minus lambda inverse transpose, then in the covariance, you're going to multiply on the left by I minus lambda inverse transpose and on the right by I minus lambda inverse. That's the covariance. And the third order moment is going to be very similar, where you take the third order moment of epsilon and you multiply it by I minus lambda inverse transpose along all three sides, because it's a three-way tensor now, it's not just a matrix. And this is the notation for this. This is Tucker product. But this is what it means. And so this S and T are precisely the M23G is precisely the set of second and third order moments of distributions in our model. And so if you have samples, so you have empirical versions of S and T, you might want to check if they lie in this model for a specific graph, and that would or if they don't, so that will tell you whether or not G is the correct graph. So one thing for people who know about tensor decomposition is that, and if not, then please ignore this, it's not supposed to confuse you. So S and T have a simultaneous rank and CP decomposition. So S can be written like this. So this omega I2 is the diagonal entries of this matrix omega-2, and AI tensor power 2 are the columns of this matrix I minus lambda inverse. And T has the same, but with omega I3 and AI tensor power 3. And this is simultaneous CP decomposition because they use the same vector as AI, which is nice. So, okay. So the only reason I'm putting this here is that now some questions that we can ask are, what are some constraints in the S and T that hold if you know the graph? So given a graph, what are the constraints in S and T? And why is this important? Well, because if we look at the previous slide that had these two graphs, so for this graph, this will be one constraint that holds this. So this, for example, will be S12 times T111, S11 minus S11 times T112. That will be 0 for this graph, and this will be non-zero for this graph, right? And by the way, this is actually the determinant of a 2x2 matrix with rows S12 and S11, and the second row would be, I guess, S11, T112, T111. So this says that some matrix has rank 1, some 2x2 matrix has rank 1 in this case, but it doesn't have rank 1 in this case. And we can, if the graph is a polytree, so this is very complicated, but the takeaway is that if the graph is a polytree, so a tree, the underlying uncorrected graph is a tree, then the constraints are exactly given by forming some matrices and imposing that they have rank 1. So the constraints are saying these matrices, which I will explain how to form, have rank 1, and also some specific entries are 0. But this characterization was also used later by people to provide a more efficient algorithm for recovering a polytree that has a good high-dimensional consistency. And in current work with my master student Cole, we actually have equations that describe the model for any directed acyclic graph. And it's also given by rank constraints, but they're not rank 1, they're higher rank. So the rank is basically the size, size of the parent set that you look like something like this. But they're just higher ranked constraints, which is very nice. Because if you want to check these computationally, it's easier to check if a matrix has low rank than to check if some crazy polynomial equation vanishes. Okay, so I want to say a little bit about what happens if there are hidden variables and what happens if there are cycles. So if we have hidden variables, we have the following setup. So here's our original structural equation model. Suppose that the variable 1 is actually unobserved. Then what we do is we would put this part here into subsume it into the noise. So we would have x4 is now some linear combination of x2 and x3 and some noise epsilon 4 tilde. And here we have epsilon 5 tilde, but epsilon 4 and epsilon 5 are no longer independent. They are dependent. And in the graph, we're going to add a bidirected edge that exactly says that there used to be a variable here. There is an unobserved variable that affects both 4 and 5. And now we have vertices, edges, and bidirected edges. And the bidirected edges tell us which noise terms are not necessarily independent. Okay. And there could be a more complicated situation where there is an unobserved variable that is affecting more than 2 nodes, maybe 3 nodes, like this. So if 1 was unobserved, then we could actually add a 3-directed edge or any multi-directed edge. And we might want to be able to learn those edges as well. So again, here, epsilon 5 is independent of epsilon 2 tilde, epsilon 3 tilde, epsilon 4 tilde, but these red ones might not be independent among each other. And now we will use the kind of graph that we use is one that has vertices, edges, and multi-directed edges, H, which I guess is H for hyperedge, but we call them multi-directed edges. And so how do we learn these models with hidden variables from observational data? You can again use overcomplete ICA, which actually doesn't guarantee converges to a global optimum, or you could learn the graph sort of in a more combinatorial manner. But most of the methods that do that, they actually learn bidirected edges. So if this was the graph, they would actually learn this graph that has 3 bidirected edges instead of 1 3-directed edge. And the reason is that if you are in a Gaussian setting, you can't distinguish between these two. And I think people are just used to looking at graphs with bidirected edges, which is why they aren't necessarily looking at these multi-directed ones. And so, so we give a very simple way to actually distinguish these two cases using higher order cumulant information, which I'll tell you in a second. And I don't have it here, but in current work with Matthias Dirken and his student Daniela Skoda, we actually have a method that learns a graph with hidden variables from higher order moments and cumulants directly. Okay, and so so let me try to explain this. So what is a cumulant? And maybe, okay, if you know it, that's fine. If you don't know it, a cumulant is basically like a moment. So it's like the expectation of the product of x's, but you have to adjust it a little bit. Okay, so That's what the cumulant is. And we show that if you take a cumulant, so the kth cumulant of vertices I1, I2 through Ik, it's 0 if and only if there's no common ancestor of these vertices. So that either there's none of these situations. There's no vertex, observed vertex that points to them, and there's also no unobserved vertex that points to them. So that's when this vanishes. And that gives us a really simple way to distinguish between these two scenarios. Okay, so in this setting, the cumulant of 2, 3, 4, the third cumulant of 2, 3, 4 will be non-zero. But in this setting, the third cumulant of 2, 3, 4 will be 0 because they don't have a common ancestor. And so what we can do is we can build on the algorithms that already exist, which learn a graph with bidirected edges, and just sort of correct them to say, oh, by the way, this is not 3 bidirected edges, but it's 1 3-directed edge instead. Okay, so this is a very simple way that we can use algebra. Okay, so I don't have time to sort of go through this algorithm, which I just described very quickly, but yeah. Oh yeah, and this is what I mentioned on the previous slide, that we also have now a newer algorithm that learns the graph using only cumulant information. Okay, I will skip through this or be on time. So the last thing I wanted to say is the cyclic case. So can we still uniquely learn a directed graph in a non-Gaussian, near non-Gaussian setting, and what algorithms can we use? And the first thing that's very interesting is that if there are cycles, we actually cannot learn the graph uniquely. So in the acyclic case, you can, but in the cyclic one, you can't. And here's the reason, basically. So suppose you have this graph, x1 is something times x4 plus x1, and so on. So you have this graph. Here's the model corresponding to this graph, and here's the opposite direction. Okay, so what you can do is you can take these equations, divide by the lambdas, and move the noise terms on the other side to get these equations. And so now you have a structural equation model that corresponds to this graph, which holds. These equations also work for this graph. Okay, and these epsilons are independent. And so if you were to observe data from this model, you will not be able to tell these two models apart. So they are equivalent in this setting. And we have a characterization for when two graphs are equivalent in the linear, when they give rise to the same linear non-Gaussian model. And it's precisely by taking some vertex disjoint cycles. We take a bunch of cycles in one of them, reverse their directions, and change. You have to change some other things as well. So if there was an edge that was pointing to one of the cycles, so if VI was pointing to VJ, where VI wasn't in the cycle and VJ was, then you have to change VI to point to VJ minus 1, the previous vertex in the cycle. So this is something called, you're preserving the P adjacencies. So if you have heard this term. So for example, 2 here points to 4, but because you're reversing the cycle 2, 3, 4, now 2 has to point to 3, which is the original parent of 4 in this cycle. So in any case, it's a very easy way to characterize when graphs are equivalent. Okay, and so okay, I'm very much out of time, but I wanted to talk about sort of an algebraic method for learning cyclic graphs as well. There do exist methods for learning cyclic graphs, and they're also based on ICA, independent component analysis, but we were able to devise a method that's based on higher order moments for a specific set of graphs that are as follows. So maybe I can just define a set of graphs in the next minute. So you, first of all, if you have a cyclic graph, you can define something called the strongly connected components, which are sets of vertices that such that there is a directed path between every two vertices. So these are maximal such sets. And the rest of the graph can be split up into these components, and there are the arrows that go between components go in one direction. So it's kind of like a DAG of these strong components. And then you have a topological ordering. So for example, 1, 2, 3, 4 comes before 9, 10, 11, which comes before 5, 6, 7, 8. And our algorithm works for graphs where these strong components are single cycles. So here we have 1, 2, 3, 4, but there's no edges between 1, 3 to 4. There's no 2 to 1. It's just a simple cycle. And then all the other edges between components could be anything they want to be. Okay, so anyways, we can learn such a graph. And since I'm out of time, I will have to skip this part. But basically, we can identify sort of root cycles or root nodes by algebraic constraints, which are just sort of 2 by 2 and 3 by 3 matrices that we have to check their rank. And we can do this successively until we have identified all of the strong components and their topological ordering. And then afterwards, we can sort of learn by doing regression backwards in this topological ordering. We can learn exactly how they're connected, and using some additional algebraic constraints, and really just algebra, we can find all of the edges and all of the weights. I'm very excited. I'm very happy to talk to you about this offline. Okay, so since I'm out of time, I'll conclude with this. So we discussed linear non-Gaussian causal models and how to learn them using second and higher moments. And there's a lot of questions left to do. For example, we don't have an algorithm to learn all possible cyclic graphs, just a subfamily of them. And maybe there are some interesting algebraic constraints on the moments that will help us do that as well. Thanks.
Thanks, Elena. We have a bunch of time for questions, so if anyone has some.
So in this equivalence with cyclic graphs, I mean, you had this characterization of equivalent graphs, but what did equivalence mean?
Right. So they give rise to the same linear non-Gaussian causal model. Right. Yeah.
Yeah, using all of the moments.
Yeah, you don't even need to talk about moments. Basically, you can show that if you take a random vector that satisfies the model for this graph, you can do a similar thing to here. So, okay, so here I'm skipping some details. You have to assume that the lambdas are all non-zero. So if the lambdas are all non-zero, then you can express the entries of this random vector as with linear structural equations that corresponds to this other graph.
Yeah, I see. Yeah, it's essentially extending the trick in this slide.
Exactly. Yeah.
Yeah. Okay.
I have a question. You presented a theorem based on the cumulants to distinguish between like a tri-directed one and and then there's also, when you presented the definition of cumulant, it reminded me of the second and third moments from before. I was wondering if there's any connection.
Yeah, so the cumulants are, so, okay, here I'm assuming that, I didn't say this, I should say, so I'm assuming the entries of my random vector have mean 0. And so, but regardless, one of the things that is nice about cumulants is that if you have independent random variables, then the joint cumulant will be 0. So you know how if x and y are independent and have mean 0, then the expectation of x times y will be 0, because it's just the expectation of x times the expectation of y. But if you take now the fourth order moment of x and y, so if you take, for example, e of x squared y squared, even if x and y are independent, that won't be 0, because it will be e of x squared times e of y squared. So now if you imagine a whole random vector of independent entries, and you take its fourth moment, it won't be diagonal. So there will be these like off diagonal entries like IIJJ that won't vanish. But if you instead took the cumulant, which exactly adjusts for this, look, it's just subtracting all of these pairwise ones, it will correct for it and it will be diagonal. So this fourth order cumulant of a random vector of independent entries will be diagonal. So it's only non-zero entries will be the I entries. And so that's why we use cumulants specifically for these, because in these models we have the random vector epsilon and it has independent terms, and that's what we get. So just get all these zeros. Yeah, so cumulants seem appear to be more useful in those settings.
Well, any other questions?
I have like a somewhat vague question, but so there's this work on nested Markov models where you have, I mean, because these Markov models, like in a general case, like non-parametric, people looked at constraints as conditional independent constraints, but then there are these generalizations where the graphical structure also gives you like these Verma constraints and other equality constraints.
Mm-hmm.
And in parametric models, it must kind of be the same, that some of these parametric constraints, they are conditional independence constraints, and some are, something else, right? So have you like looked at the connection to these nested Markov models?
No, and I think it's very interesting. So one thing that I have wanted to try is once we get all of the equations, then sort of eliminate all of the third order moments from the equations and see if we'll get the Verma constraints in the Gaussian case. Like maybe they somehow come from equations that use the higher order moments, but because for Gaussian those are not meaningful, then you kind of if you eliminate them, you get the Verma constraints. Because the Gaussian case is, it's linear but Gaussian. So that's one thing I was going to try. Maybe there's some more non-parametric questions. I don't know.
Yeah.
Okay.
Great. So our next speaker is Soren Mogensen. So he's going to be talking about causal learning and stochastic processes.
Thank you for having me. So I will also talk about how to learn graphs, but in this case, the graph will represent a multivariate stochastic process. So in Elina's talk, each node would represent a random variable, but in my talk, each node represents one stochastic process, so one coordinate process in a multivariate stochastic process. And in the classical case, people look at conditional independence and tests of conditional independence among random variables to learn these graphs, and we will look at this local independence instead, which is a notion in continuous time processes, or in time series we'll look at Granger causality. And actually today I'll talk about Granger causality because like probabilistically everything is a bit more simple when you don't have continuous time. And this is John work with Nistika and then with Dan Malinsky. So as I just said, I mean, we want to start from just observation of a random vector, and then output a causal graph. And what people have been doing, one of the things that people have been doing is using tests of conditional independence to output an equivalence class of graphs. So compared to Elina's talk, I'm going to be in this general setting all the times, not making any parametric assumptions. But in this talk, we will consider a multivariate time series, and we want to output a causal graph where each node represents one process in this multivariate time series. And a big chunk of this talk, we will look at essentially so what we call weak equivalence. So normally the goal is to output all of the graphs that could represent the granular causalities that you observe in the data, but we will show that this is essentially very difficult. And for this reason, we will relax this notion to arrive at this at these weak equivalence classes. So say we have data from a multivariate time series. So this is a stochastic process in discrete time. And I have this notation x alpha t. So t is the time index, it's an integer. And alpha is in a finite set v, which is just the index set of the coordinate processes. So I have some example data here where I have 6 coordinate processes, and I have observation over time. But as I said, I mean, this is I'm thinking about this as being in discrete time, but it could also be in continuous time. And then a bunch of notation to define this notion of range of causality. So I take D to be a subset of V, and then I have this set X dt, which those are just the random variables in D at time t, right? And I also have xd smaller than t, which is just the past of xd. And to define, so we're ready to define this gradient on causality. And the important thing here is that we'll just use it as people have been using conditional dependence in the classical case. So we'll just think of it as a ternary independence relation. So I take 3 subsets of B, so 3 sets of coordinate processes A, B, and C, and I say that A is gradient on causal for B given C if I have this conditional independence. So I'll expand on this. So I'm looking at X xb at time t, so that's the green part, and I'm asking if I condition on the past of C, so that's the yellowish part, do I get any more information from also having the past of processes A? And if that's not the case, then, I mean, this is formalized using this conditional dependence, right? And if that's not the case, then I say that A is gradient on causal for B given C. And as I mentioned before, this is analogous to conditional independence in continuous time process. And this gives me an independence relation which is not symmetric. Of course, conditional independence is symmetric in A and B, but this is not symmetric in the sense that A being gradient on causal for B given C does not imply that B is gradient on causal for A given C. So this is the thing I want to test from my data and then output all of the causal graphs that are in correspondence with what I observe in my data. So we'll start from defining a Granger causal graph. So this is a directed graph. It can be cyclic now. And V is, again, this index set of my coordinate processes. And then I define an edge set E. Like this, I take 2 processes, alpha and beta, and I leave out the edge from alpha to beta, if and only if I have this gradient on causality. So I'm asking, so I'm essentially, you can think of this as saying, or maybe I should say that the thing on the right-hand side of the biimplication, that's a gradient on causality statement, right? So this is saying that alpha is gradient on causal for beta when I condition on everything but alpha. So if I'm trying to predict what happens at the next time step in beta, and I have all the information except the past of sorry, I'll start over. So if I'm trying to predict beta at the next time step, and I have all the past information except the information the past of alpha, then alpha doesn't add anything. In this case, I leave out the edge. And so in this way, I construct my graph D, and I call this the Granger-Causal graph. And it's possible to, from this graph, to read off more general Granger non-causalities, which is quite interesting, right? Because you input only Granger non-causalities of a very specific type, but then you can read off more from it, and this is what is known as a global macro property. And for this, we need delta separation or mu separation, and those are analogous to D separation in DAX. So in this talk, I'm not defining what mu separation is, but it's completely analogous to D separation, very closely related. So just think of this as, you take your three sets, A, B, and C, and you just have your graph, and your computer can check if there's mu separation or not. And a bit of notation, we use this I of D notation to just denote the set of mu separations in this graph D. And under various conditions and various models, you can prove that we have this theorem, which is known as the global macro property. So again, X is a multivariate time series, and D is its Granger-Causal graph as defined before. And if I have mu separation, so B is mu separated from A given C, this implies that A is Granger non-causal for B given C. So this is a graphical representation of this notion of Granger non-causality. Or if we use a very shorthand notation, this I of D is a subset of I, where I is just the set of triples such that Granger non-causality holds. And the idea is that, as mentioned before, you could have this I model could be generated by Granger non-causality, but in other kinds of models, it could be local independence. And in some models, it could also be directed conditional information or other notions of independence. And in this talk, we will also assume that faithfulness holds, which is the opposite implication. So we're essentially assuming for the remainder of this talk that I equals I of D. So this is the very nice case where the Granger non-causalities that I observe in my data, they are encoded exactly by this mu separation. So now the task is to, from observation of this I set, how can I construct all the possible Ds? And one complication is the fact that we may not observe all of these coordinate processes. So we want to be able to account for the fact that some of the coordinate processes are unobserved. And of course, in a stochastic process, you may have partial observations in different ways, right? But the specific kind we're talking about is the case where some of these coordinate processes are fully unobserved. So in this plot, two of the coordinate processes are unobserved for the full length of observation, right? So the four remaining coordinate processes are fully observed, but two of them are just not observed. And as is common, we're not making any assumptions about the number of observed processes or how they connect to the observed part. We just want to account for the fact that there might be unobserved processes. So the first step is to find a marginal of D. So we want a graph G where the nodes are the observed nodes O, such that for all these A, B, and C that are subsets of O, I have mu separation in D, if and only if I have mu separation in G. So this would be enough reason to call this a marginal of D, right? In this mu separation setting. And I also want to be able to construct this G from D. And this is a typical thing in also the DAG-based causal learning. And one can use a so-called latent projection. And this gives us a slightly larger class of graphs known as directed mixed graphs. And instead of defining this latent projection, I'll just show you an example. So we had this graph on the left before, but two nodes are unobserved. And using this latent projection, I get the graph on the right. And you can see, as we saw in Elina's talk, that these they act as confounders, right? And those are represented by these bidirected edges. Okay, so from this, we essentially want to learn. I want to test gradient causality, and then I want to output all of the causal graphs that could correspond or generate the independences that I'm seeing in my data. And for this reason, I need to understand these Markov equivalence classes. So I take two DMGs and I say that they're Markov equivalent if they agree on all mu separations. And this is what we, in principle, can learn from tests of Granger causality. So again, we're assuming faithfulness. So the mu separations are in one-to-one correspondence with the Granger non-causalities, right? So testing Granger non-causality, I can never go further than learning this Markov equivalence class. So it's important to understand what this Markov equivalence class looks like. And one issue that arises is the following. So one can prove that just deciding Markov equivalence of these directed mixed graphs is computationally hard. So it's co-NP complete. And this is pretty unfortunate because it seems way easier than learning a graph, because this is the problem where I just give you two DMGs and I ask if they're Markov equivalent. These are two known DMGs, right? But it still scales very poorly. That's what it means, right? But this also implies that many of the computational problems that you would face when working in this framework, those are also difficult. I think, yeah. So, for instance, it implies that you cannot find a polynomial time algorithm which can output the correct Markov equivalence class, even in the Oracle setting where you don't do any statistical tests, but you just happen to know which Granger non-causalities hold and which do not. So it means that learning is very difficult, right? And actually, this result also holds under certain sparsity constraints on the graph. So just saying that there's a fixed number of parents, that's not going to fix this issue, unless it's a very small number of parents. Okay, so this tells us that we need to do something else, and for this reason, we introduce this weak equivalence. So now we take some fixed integer k, and we just say that these two graphs now k-weakly equivalent if they agree on all mu separations such that the C set, the conditioning set, is sufficiently small. And this is the generalization of Markov equivalence, because n weak equivalence is of course Markov equivalence. So instead of trying to compare the graphs on everything they encode, they say, okay, we just say that they're equivalent if they agree on all the separations with small conditioning sets. And one reason to do so is the fact that when you do statistical tests, if you have a large conditioning set, you don't have any power anyway. So you actually, like for practical purposes, you need to learn the graph from tests with small conditioning sets anyway. And one more reason, algorithmically, is that essentially when you keep this k fixed, then the graphs may grow in size, right? But this kind of solves all of our computational problems, or at least we can get into the realm of polynomial time algorithms. And I mean, just from the definition, it follows that if I take k1 smaller than k2, then if two graphs are k2 weakly equivalent, they are also k1 weakly equivalent. So you get this hierarchy where choosing a k just lets you choose how granular your graphical modeling is going to be. And one can then prove a very nice characterization of these k-weak equivalence classes, because I mean, starting out, we don't know what these k-weak equivalence classes look like, so it's and we somehow want to take our tests of Granger-Norm causality and then output the set of graphs that correspond to what we see in the data, but we also want to kind of summarize that set of graphs. And so essentially we want to find a nice representative of a k-weak equivalence class. And it happens to be the case that each of them contains a greatest element. And I'll show you an example of what I mean by that. So for instance, the graphs 1, 2, 3, 4, 5, 6, they constitute a 4-weak equivalence class. So a 4-weak equivalence class in this case is also a Markov equivalence class. And one of them, and this will always be the case, is a greatest element in the sense that it's a supergraph of all the equivalent graphs. So in this case, 1 is a supergraph of the other graphs, because if I take any other graphs, say 5, and I take any edge in 5, say the bidirected one alpha to beta, that's also going to be in 1, right? So to summarize this graph, I can take the graph in 1, the greatest element, and copy paste it, and then I can just leave an edge solid if it's in every member of the equivalence class. So say the directed edge from gamma to delta, that's in all of them, and then let it be dashed if it's in some but not in others. So the directed one from gamma to beta is in this one, but it's not in that one. So in this way, this graphical object that we call a directed mixed equivalence graph summarizes the entire equivalence class. And this is essentially what can be learned from tests of Granger-Norm causality. And of course, one should note that these equivalence classes, they don't need, I mean, they don't necessarily have a least element. So in this case, this means that you cannot remove both the directed edge from gamma to beta and the directed edge from delta to beta. That would not be equivalent. So this edge being dashed is essentially a local information. You cannot remove any combination of the dashed edges and retain equivalence. Okay. So one observation is the fact that when we use so when we try to learn a graph from data, we are often interested in a sparse setting, right? We're kind of assuming that there's some sparsity, because if there's no sparsity, then we would just get out a complete graph, right? So one can see that in somewhat, and one can somewhat quantify this, but this is still work in progress, that that if I'm in a somewhat sparse graph, the difference between, say, the difference between the information in the Markov equivalence class and in a k-weak equivalence class may not be that large. So this is just one such example. So say that my fully observed graph is in A. So this is the graph D. And to the right, I have the directed mixed graph when marginalizing away the processes E and H. And then in C, I have the greatest element, or the directed mixed equivalence graph, of the Markov equivalence class. So this is the maximal information I can get out from tests of Granger non-causality. So in this case, k is equal to 10. Then if I reduce k to 3, I get the greatest element of the k-weak equivalence class corresponding to k equal to 3, right? And the difference between these two is not that substantial. The only difference is the bidirected edge from A2 to A7. So of course, I would always get more information, or I would get a smaller graph rather in the graph on the left. But in this case, and you can see this in many sparse examples, the difference may not be that large. So just to sum up the idea of this, so you take this partially observed data where some coordinate processes are unobserved. You conduct some tests of Granger non-causality, and it's of course also a good question how to do that well. But let's just assume that we do have good tests, and you get this observed I. Those are just the Granger non-causalities that you observe in the data. And using this graphical theory, you can characterize these weak equivalence classes. So you can choose a value of k. You can also choose it depending on how much computational power you have. And you can, for any value of k, you know that there's going to be a greatest element in this weak equivalence class, and you can use that to summarize the entire equivalence class. So essentially, maybe I already said this, but one reason to look at these weak equivalence classes is of course the fact that these computational problems are hard. Otherwise, of course, it's somewhat of a theoretical problem, because I mean, if you have large graphs, then a polynomial number of tests with a large exponent may also be unfeasible, right? But at least using this weak equivalence, you kind of get a hierarchy of granularity. So when you increase k, you get, I mean, it becomes more expensive computationally, but you may get more information. And maybe I'm running out of time, but maybe I can just show you as the very last thing that you can essentially get a lot of, I mean, you get a lot of structure in this hierarchy. So let's, so this is just the definition of these k-weak equivalent, these k-weak equivalence classes again. But we can think of this k as a parameter, and we can change it, right? So I can, for each k, I can find, so now I'm just fixing v, right? And on the next slide, v is going to be just 4 nodes. So it's just 1, 2, 3, 4. And for each k, I can list all the greatest elements of each Markov equivalence class, right? And then I can do this for each value of k, and you get a lot of structure there. So on the next slide, what I'm doing is essentially connecting the pairs gk. So this is, so the pair gk means that it's that G is a greatest element of its macro equivalent, or sorry, of its K weak equivalence class. So I'm connecting GK and G minus at K minus 1 if G is equivalent with G minus at K minus 1. So I don't think this made sense to anyone, so I'll just show you on the next slide. So this is so this requires some explanation, but now on each level you have, so on top level it has a 3, right? So this means that K is equal to 3. And then imagine you have a bunch of nodes where each node represents a greatest element of a 3 weak equivalence class. So if you take the graph AD, then this downwards edge means that on the 2 level, this graph AD is 2 weak equivalent with the AC graph. So you get this poly tree where once you go down, because then you're reducing the value of K, right? So once you go down, you're essentially just collapsing these weak equivalence classes, right? So you start from the top, which is macro equivalence, but then when you go down, you collapse them. And I should say that this is, of course, only a tiny part of this hierarchy on 4 nodes. It's huge. So I think I've spent my time and maybe some. Thank you for listening.
Thanks, Dr. Mogensen. That was great. I think I'll start with a question. I've been wondering, like, what's the relationship between Granger causality and just regular causality? I mean, my guess would be that Granger causality identifies all the nodes in the Markov blanket as causal. Is that true?
Yeah, I think so. In my perspective, Granger causality, I mean, the name is really bad because the way I'm using it here, there's nothing really causal about it. It's analogous in this work to conditional independence, right? And conditional independence, people would never think about that as being causal, right? I mean, you may define something like a causal graph, you define something like interventions, and then you just observe, okay, I can test conditional dependence and I can recover this causal graph, right? And I would think of it the same way. Actually, the talk I gave today, I would say there's nothing really causal about it. Because this gradient on causality, it's just an independence relation that I'm using to learn something about some graphs. But of course, the reason to think about like confounding and things like that, that's of course from causal reasoning. And essentially, if you have, so Elina had these structural causal models, and if you have like a dynamical version of those, then something like this would hold. So essentially, if I just take like a structural causal model, but now I have, nodes over time, then that model would satisfy this. So what I'm learning is really a causal graph in the normal sense. But I would say that this Granger causality really has nothing to do with causality. It's just, an independence relation. And I think that's somewhat of a, I mean, because if you look to many applied papers, they'll say things like, yeah, I mean, we know Granger causality is not really causality, but causality is hard, so let's just do this, right? And then they learn this graph, but they never really explain what they mean by causality. And I also didn't explain that, but today. But if I were to give a causal interpretation, I would use something like a structural causal model. So I mean that was a long answer. I hope it answered the question.
That was good. Yeah, thank you. Any other questions?
I have one follow-up, and maybe I'll start off with first one. So you mentioned how you're interested in like a maximal representative from every Markov equivalence class. I was wondering if to find that representative, you need to generate every element, or if there's a smarter way to do it, like to identify.
Yeah, that's also a very good question. You don't need to generate every member, but finding the greatest element is also computationally hard. So if you want to find a the greatest element of a k-weak equivalence class and you keep the k fixed, then it's not hard. Then it's polynomial. But let's say you want to find the greatest element of the Markov equivalence class. The problem is now kind of the k is growing all the time when you get more nodes. So that's a hard problem. And that's one of the reasons I started looking at these weak equivalences, because it's not very nice to have this. I mean, the theory works out well for this Markov equivalence, but it's very difficult to work with, because even just taking a graph and finding its, maximum representative, that's a hard computational problem.
Maybe you can find a class of graphs for which the k-weak equivalent, like k-weak equivalent is the same as Markov equivalence. Is that what?
Yeah, it's not something I've thought about. Yeah, that should be possible. Yeah, that's a good idea. Maybe I should also add that this existence of a greatest element is not something you'll see in other classes of graphs. Like if you have, I mean, if you define two DAGs to be Markov equivalent if they have the same d-separations, then those equivalence classes, they don't have a greatest element. For one reason, because you would need cycles, right? Just in the simple examples that Elina had with two nodes, right? You had pointing that way and pointing that way. So to have a greatest element, you would have a cycle, right? So this existence of the greatest element is not something. I mean, it's not. Yeah, it's not something you see in other classes of graphs. For one reason, because of this acyclicity.
And is it easy to find which vertices, which edges are solid and which ones are dashed?
Yes, that's easy. If you have already the greatest element, then that's easy.
I can check if that's some Ranger non-causality statement.
Sorry.
You just know which statements to check for.
Yeah, and I mean that's a purely graphical thing, and yeah, I mean it's not obvious that it's easy, because essentially you have like the first graph, then you remove an edge, and you want to know if they're still equivalent, right? But it just happens. Yeah, one can show that that's actually easy. Yeah.
Any last questions for Swan?
Maybe the last one at the end. I know it's late for
Okay.
Marcus.
Yeah, we'll have some a little bit of discussion at the end too. So yeah, our final speaker is Pardis Samnani. She's a PhD candidate at UBC. So go ahead, Pardis.
Thanks. So I'm going to just share my screen. Okay. Can you see my screen now? Okay, nice. So hi everyone. Today I'm going to talk about causal structure learning in directed, possibly cyclic graphical models. This is a joint work with Elena. So I'm going to start by telling you what the problem is that we are considering here. As you all know, determining the causal structure between different random variables that we are interested in is a central task in many disciplines. And as it has been mentioned today, the causal structure we often model by a directed graph where our vertices are the nodes, are the random variables that we are interested in, and a directed edge between one vertex to another shows a direct causal effect between the corresponding of learning this causal structure from observational data. A simplifying assumptions that many people use is that directed graph, the causal graph, is acyclic, meaning that it doesn't have any directed cycles, or in other words, feedback loops. However, in reality, sometimes these directed cycles or feedback loops do exist. This might happen in gene regulatory networks, in climate science, in economic processes, and so on. So I'm just going to give you an example of this directed graph in a like real life setting. So for example, we know the emission of greenhouse gases is a cause for the rise in temperature of Earth, which is itself a cause for the melting of the permafrost, which is itself a cause for emission of greenhouse gases here. So like here we have an example where this feedback loop happens in our model. Now, our work is basically focused on learning the causal graph with when we also allow for these directed cycles. So in the next slide, I'm going to be more formal and actually introduce what our setting is, what our assumptions are, and what our approach is going to be. So our assumption is that we have observed some independent and identically distributed samples.
I think the slides aren't, like, we're on the title slide.
Oh, no. Okay.
At least on my screen.
Maybe I should. What about now?
Yeah, now I see our setting and approach.
Oh, okay, good. Maybe I should have just exited the full screen then. Okay, thanks. So this was the previous slide. Basically, the main thing was like this cycle here in this model of climate science. But now I was going to talk about this next slide, which is our setting. So yeah, we assume that we have observed these IID samples from some unknown distribution P, which is in the graphical model of and faithful to the directed graph that we are looking to discover. Let's call it G star from now on. And well, we assume that we have some way of inferring all the conditional independence statements of the distribution by looking at this observational data. Now, the other assumption that we have is that we have no latent variables. That is, if we are observing n random variables, then n is the number of the nodes of G star that we are looking to discover. The notion of graphical model faithfulness Markov equivalence that I'm going to use in this work is, I guess, a little bit different maybe from the previous stuff. So I'm just going to introduce to make sure we're on the same page. So for an undirected graph, we have this nice notion of separation, where we say a vertex A is separated from a vertex B given a subset of vertices C, which must not include A or B. And this happens if all the paths from A to B contain at least one vertex from C. So C separates A and B. Now, in the directed graphs, we have just somewhat similar notion of separation, which we call deseparation. My understanding is that this notion of deseparation is different from, for example, mu separation that was used in the previous talk. Please correct me if I'm wrong, but deseparation is what we are going to use in this talk. And so let's say that X is an n-dimensional random vector with distribution P. When we say that the distribution P is in the graphical model of and faithful to the graph G star, we mean that for any two vertices A and B in the vertex set of G star and any subset of vertices C, we have that A is deseparated from B given C in the graph, if and only if the random variable XA is independent from XB given XC. So basically our assumption here is that the set of deseparations of the graph exactly encode the conditional independence statements that arise from the distribution. And so we say that two graphs are Markov equivalent if the set of deseparations that arise from these two graphs are exactly the same, and this actually happens both for directed acyclic graphs and for directed cyclic graphs. And then there are sometimes a cyclic graph and an acyclic graph, which basically generate the same set of deseparations, and we'll see that in the next couple of slides. So here we, of course, allow for directed cycles. We are working in the full non-parametric setting. And we define two goals for ourselves. The first goal, which is the focus of this talk, is to use this observational data to recover all the structures that all the graphs Markov equivalent to G star have in common. So basically, these structures very uniquely determine the Markov equivalence class of G star. And then the second goal is to use these common structures to find a graph in the Markov equivalence class of G star, so a representation of this class. But this part I'm not going to talk about today. And our approach for this Markov equivalence class discovery test is an extension of the hybrid approach that was previously used in several works in the acyclic setting. So I guess that's the high-level overview that I just wanted to give about this algorithm, and then a little bit of more details. So basically, for discovering the Markov equivalence class, we consider some certain objects, and we assign a score to each object, and we do it nicely so that whatever object that optimizes the score actually characterizes our Markov equivalence class too. So the first question is, what are those objects? Those objects are partially ordered partitions. And to actually say what we have considered this, we should make a simple observation here. So consider any directed graph G star, like the one that you see in this slide, and consider the following equivalence relation on the vertex set of G star. So for two vertices I and j, you say that I is equivalent to j if and only if they are either the same thing, or there is a directed path from I to j and a directed path from j to I in the graph G star. And so you can easily verify that this is an equivalence relation on the vertex set of G star. So it gives rise to a partition on the vertex set. And each block of this partition we call a strongly connected component. So in other words, a strongly connected component would be a maximal subset of vertices of G star, where every vertex in this subset can be reached from any other vertex in the subset via a directed path. So in this G star that you see here, for example, these three components are the blocks 1, 2, 3, 4, then 5, 6, 7, then 8, 9. And then in addition to this partition, I want to add a partial order. So for two components C1 and C2, two strongly connected components C1 and C2, I say C1 is less than or equal to C2 if and only if there exists a directed path from any vertex in C1 to any vertex in C2, or that C1 or C2 are the same thing. So again, back to our example, this is the non-trivial pairs in the partial order. 5, 6, 7 is less than or equal to 1, 2, 3, 4. Why? Because take any vertex in 5, 6, 7, let's say 5, it has a directed path to any of the other vertices in 1, 2, 3, 4. And also 5, 6, 7 is less than 8, 9, because again, 5 has a directed path to 8, to 9. The same thing is also true about 6 and 7. So we saw here that corresponding to any directed graph G star, there comes a partially ordered partition associated with G star. And this simple observation motivated us to consider our objects of interest to be basically the set of all partially ordered partitions on the vertex set 1 up through n. So that's what we do. We consider this set S, which consists of all pairs P and pi, where P is a partition of the vertex set, and pi is a partial order on the partition P. And so that's how we define our objects. Now, next step would be to define our score. So in order to define a nice score, we want to have a local characterization of Markov equivalence, because remember that optimizing this score should eventually give us the Markov equivalence class of G star. So as I think you know, we have this nice characterization of Markov equivalence in the case of DAGs, directed acyclic graphs, by Verma and Pearl. It says two DAGs are Markov equivalent if and only if they have the same V structures and the same adjacencies. Adjacencies are clear. It means the same underlying undirected graph. And a V structure is a triple ABC, where A and C have B as their common child, but A and C are not adjacent to one another. So that, unfortunately, is not true when cycles come into play. So take these two graphs, for example. Note that one of them is a cyclic graph. So in the left graph, I guess we have B, D, C as a cycle. And you can verify that they have the same skeleton, so the same adjacencies and the same V structures. The only V structure in the two graphs is ABC. However, they are not Markov equivalent because A is not disseparated from C in the left graph, but it is disseparated from C given the empty set in the right graph. And I also can give you a counterexample for the other side of this theorem when cycles exist. So I can give you two graphs that are actually Markov equivalent, but they don't have the same skeleton or they don't have the same set of these structures. So what should we do? The good news is that luckily for us, there is this theorem by Richardson in 1997, where he gives 6 conditions in order for two graphs G1 and G2, which might have directed cycles, to be Markov equivalent. Now, well, these graphs, as you can see, like these are just a lot of conditions with a lot of words, but basically each condition says that the two graphs should have the same number of occurrences for a specific kind of structure. I'm not going to go into details of what these structures are, just a couple of words. So the first sentence says that G1 and G2 should have the same P adjacencies. This is a generalization of the two graphs having the same adjacencies in the DAG case. And the second one says that G1 and G2 should have the same set of unshielded non-conductors. This is, again, a generalization of the two graphs having the same set of these structures in the DAG case. The other conditions, though, won't happen unless the graph has cycle. Otherwise, like those structures are just impossible. So that's the characterization of Markov equivalence. Now, the next question is, how are we going to use this characterization? So I'm just going to explain a little bit more about this first condition, so I can give you the idea of this algorithm. So the first condition said that G1 and G2 should have the same P adjacencies. Now, just to give the definition of the P adjacencies, two vertices A and B are said to be P adjacent or pseudo adjacent if they are either actually adjacent in the graph or that they have a common child, which is also an ancestor of at least one of these two vertices, A or B. So that's the definition of pseudo adjacency. Now, corresponding to this structure that should be common in all Markov equivalent graphs, its occurrences should be common in all Markov equivalent graphs, we define this set E1 for each partially ordered partition P and pi. So for each partially ordered partition P and pi, this E1 will consist of all pairs A comma B, such that A is not independent of B, given the set of all vertices that come before A or B in this partially ordered partition P comma pi. So it turns out that if we take S1 to be the set of all partially ordered partition that minimize the size of this set E1, then first, the partially ordered partition associated with our original graph is indeed in S1. And next, every partially ordered partition that is in S1, that is every partially ordered partition that minimizes the size of the set E1, the set E1 corresponding to that partially ordered partition is equal to the set of P adjacencies in G star. So you can assume that, well, one thing we can do to get the set of P adjacencies in G star that we are looking to basically discover is to take all the partially ordered partitions, find the size of the set E1 corresponding to all of them, and whichever partition minimizes this size will give us a set of P adjacencies. Now, the idea is to do the same thing for all the other constraints in the Richardson theorem. So corresponding to the second structure in the Richardson theorem, we define this set E2, and we define a same type of proposition. We prove a same type of proposition for it. Then corresponding to the third one, we have this third set. Corresponding to the fourth structure, we have this fourth set. Corresponding to the fifth one, we basically have a bunch of sets, n-2 of these sets. And then corresponding to the sixth one, we have the sixth set. I just want to mention that just looking back at these sets, in order to find these sets for each partially ordered partition P pi, sometimes we have to do some conditional independence testing, which isn't necessarily an easy thing to do. But I want to emphasize here that the only sets for which we actually need to do this conditional independence testing are the set E1, where we have to do n choose 2 conditional independence testings, and this set, this set here, where we again have to choose this set E3 here, where again we have to choose, we have to do n choose 2 conditional independence testings at most. So at most n squared conditional independence testing for finding the graph, for finding the score corresponding to each partially ordered partition. So anyway, as you can, I think, predict, when we have a bunch of conditional independence statements satisfied by the distribution. For any partially ordered partition p pi, we define this graphical score of p pi to be an integer vector of length n plus 2. For each component of this vector is either the size of one of these sets or minus the size of one of these sets, depending on if you want to maximize the size of such sets or minimize them. And then basically be able to compare these integer vectors, use the lexicographical order, which says x is less than y, whenever xj is less than yj, where j is the first entry where these two vectors x and y differ. And the main theorem of this section is that any minimizer of this graphical score over the partially ordered partitions with respect to the lexicographical order uniquely determines the Markov equivalence class of G star. So I think at this point, the idea of the algorithm is clear. However, there is the problem that the number of partially ordered partitions is on n vertices is basically super exponential in n. So it's not efficient to actually test all the partially ordered partitions, find the scores for them, and then compare them. So we want to do this in a little bit more efficient way, which brings us to the next slide. So a more efficient way for optimizing this score is the following. In order to do that, we first form a graph where the vertices are actually the partially ordered partitions, and the edges of the graphs between different partially ordered partitions are defined as follows. So basically, we just connect two partially ordered partitions if they differ in some slight structure. So with these three rules, we connect P1 pi 1 to P2 pi 2 if and only if partitions P1 and P1 and P2 are the same, but the partial order differ in exactly one pair. So for example, here, take this middle partially ordered partition consisting of the blocks 2, 3, and then 1, 4 separately, and with the only non-trivial pair in the order that it says 2 is less than or equal to 3. So this middle purple partially ordered partition. With this rule, this partially ordered partition gets these three neighbors. So these three neighbors all have the same partition, but for example, this neighbor here has one less order, so no basically non-trivial pair in the partial order, and these two pairs over here have one more pair in the partial order. So that's how these three edges are constructed, corresponding to this middle partially ordered partition. The other rule that we use is the following. So P2 pi 2 should be obtained from P1 pi 1 by moving exactly one element between a pair of consecutive sections. So again, back to our example, we have a pair of consecutive sections, which is 2 less than 3. And by moving one element between these two sections, we basically have to merge these two sections. So 2 and 3 get merged. And we get this new partially ordered partition where the partition consists of the blocks 1, 4 and 2, 3. And then there's no non-trivial pair in the partial order. So that's the second way of getting edges. And the third way of getting edges is if P2 pi 2 is obtained by taking out one element from one of the sections in P1 and adding that element either right after or right before that section as an independent section. So for example, again, for this middle partially ordered partition, with this rule, we get these two neighbors where we have taken out one from the block 1, 4, and in this bottom neighbor, we have added it right before 4, and in the upper one, we have added it right after 4. So anyway, we have these rules for defining a graph where the nodes are partially ordered partition, and this graph is going to be a directed graph where there is a directed edge from P1 pi 1 to P2 pi 2 when the graphical score of P1 pi 1 is greater than or equal to the graphical score of P2 pi 2. So the direction of edges will depend on the observations and the conditional independence statements that we have inferred, and thus the graphical scores that we have computed. And so based on experimental evidence, our conjecture is that if we construct such a graph, we can get from any partially ordered partition to an optimal partially ordered partition via a directed path in this graph. And if this is true, then this is the algorithm that we're going to use, which is actually what we are using in our experiments, where we start with some partially ordered partition P1 pi 1. We'll call it p hat pi hat. Then we perform a depth first search on our graph G, which is the graph of partially ordered partitions, with root p hat pi hat. And we try to find a directed path from p hat pi hat to some other partially ordered partition p tilde pi tilde, whose graphical score is strictly less than the graphical score of p hat pi hat. If this better partially ordered partition p tilde pi tilde is found, then it will become our new p hat pi hat, and we'll perform another depth first search with this root. Or if not, this means that we have found our option, and that's going to be p hat pi hat, and that's going to be the output of our algorithm. I just want to mention a couple of things about this algorithm. So in this algorithm, when we get to the partially ordered partition, in order for the algorithm to actually understand this is the optimal partially ordered partition, it needs to still do a full depth first search on the graph G with this root, which we know is the partially ordered partition, but the algorithm doesn't know it yet. But this is impractical because the number of optimal partially ordered partitions might be large. So again, in running our experiments, what we do is that we say, okay, this partially ordered partition that we are at is basically the best one. If we observe a directed path of length n, consisting of partially ordered partitions all with the same score. So if we observe the same score n times in a row, where n is some input that we give to the algorithm as a threshold, then we say, okay, so what we've observed is the best thing that we're gonna get. And of course, we can just repeat this algorithm multiple times and each time just compare the outputs and take the best as the final output. So I'm just gonna end my talk by showing you some simulations. So we have coded this graph in R. We have used the Erdos-Renyi model and the R library iGraph to generate random graphs. We have generated the d-separation of these graphs, which will be equal to the set of conditional independence statements satisfied by our distribution that we observe in reality. So because of that faithfulness and graphical model assumption that we had. And so we give to our algorithm the set of the separations of each of these random graphs as the input. Now, for each running of the algorithm, we have basically tested the algorithm on 3 different initial partially ordered partitions, as you can see here. And this is the parameter n that we have used for our algorithm, depending on how many vertices our graph has had. So with these parameters, I'm just gonna show you the results of 2 of the simulations that we had. So here we've tested our algorithm on 120 random graphs, each with 7 vertices, but with different levels of sparsity. So the vertical axis here shows the execution time of the algorithm in seconds, and the horizontal one shows the basic density of the graph, the probability of an edge appearing in the graph. As you can see, the denser the graph gets, the running time, the lower the running time of the algorithm becomes, surprisingly. And the success rate of our algorithm with these parameters is 93%, 97%, and 100% and 100% respectively. So this is the same number of vertices, but different sparsity. And finally, we have this other simulation results where we are testing the algorithm on graphs with the probability of an edge appearing equal to 0.3, but different numbers of vertices, 7, 8, 9, 10. And then again, you can see the execution times in seconds, and the success rates are almost the same, more or less, 90%, 93%, 97%, and 93% in total. So yeah, those are 2 simulations that we had. And I think with that, I can end my talk here. And thank you for your attention.
Great, thanks, Boris. I guess I'll now open it up. We have about 25 minutes for a general discussion. We can now ask any questions you have for the speakers, and then I'll have a few discussion points towards the end if we run out of questions.
But so for the last simulation, if you have a dense graph, you have very few of these strongly connected components, right? Is that why you get
Yes.
this? Yeah.
Exactly, because strongly connected components get very small, and so I mean, each component gets very big, but the number
Yeah.
of them gets small. So some of the structures basically just disappear.
And maybe I can ask one more question. Do you know of any, because you have this assumption of the global macro property or the deseparation macro property and faithfulness, but do you know any global macro properties that would hold for these cyclic graphs? Because I only know one in the linear cyclic case, but are there like general ones?
No, I also know that linear cyclic case, which I think is that one by Spiritus, if I'm not mistaken. But yeah, the only one I know is also in the linear case. I know that this, the fact that if we take a structural causal model, the fact that it's Markov to its causal graph, which always holds in the acyclic case, doesn't hold in this cyclic case. And that one I know that holds when the structural causal model is linear or that our variables are discrete. And in some other minor cases that has been proved. But yeah, further than that, yeah, no, I'm not aware of.
Okay, thank you.
No problem.
Vince, you had another question for Soren, right?
I mean, it's a kind of general thing. It's building on your discussion point about Granger causality. As in Soren's answer, you mentioned that I mean, you've been saying this too. You don't like Granger causality, associative causality. And Soren's answer was that it's more of a conditional dependence. One difference, though, is that conditional dependence is symmetric, right? And Granger causality, because of that time history, it's not symmetric. And I was curious, like in a case with an asymmetry, let's say like, A Granger causes B, B does not Granger cause A. Like, do you weight that at all as a notion of causality? Because like intuitively, the cause preceding an effect and helping predict it, like, I don't know, it's not super rigorous, but it holds some intuitive ground, at least for me.
Yeah, maybe I was also being a bit imprecise. So what I meant was that if you use these structural causal models, you have this notion of an intervention, right? So when I think about a causal model, it doesn't only give you an observational distribution, it gives you a collection of distributions, and it will tell you what happens when you intervene, right? There's some exogenous intervention, but the model will still tell you what the result of that will be. So let's say that's like a vague definition of a causal model. Then Granger non-causality, or the way people are using it, it's just properties of one distribution. So it's just a way to describe a distribution, and it's something you can test in a distribution. But in my perspective, it's not enough to define a causal model. And I think one of the reasons, and of course, you're correct in saying like this thing of, I mean, it being asymmetric makes it look more causal. And I would say even more so does the fact that if you observe all of the coordinate processes, then you can use tests of Granger non-causality to identify the graph, like the causal graph. So in my framework, if you don't have partial observation, you have full observation, then you will get out the true graph. And this is essentially why Clive Granger used this word, like this causality, I think, because he was saying like, well, if I have all of the information, then this should give me the right structure, something like that. But I think that's pretty unfortunate, because then once you don't have all of the information, it's just something you can test from your data, but it's not something that's enough to give you the causal graph, say. So yeah. So I think that's one of the reasons for the confusion, or like this why people are using it this way, that if you just assume that you observe all the processes, it seems like a very reasonable notion of causality, and it probably is, and it does correspond. In that case, when you have full observation, it corresponds very closely to like this um, interventionist definition of causality. Um, so I think that's the origin of the confusion in a certain sense.
Makes a lot of sense.
And I mean, and Granger was aware of this. I mean, I think in some of his papers, he wrote that this Granger causality, it's important what your conditioning set is. So if you don't observe all of the relevant information, then it's not a causal notion.
Good. All right, I'll let Praveen.
Yeah, Praveen, you can go ahead.
Yeah. Hi, Soren. So I was one of the speakers yesterday, and I'm going to keep my video off because that seemed to cause a lot of interference. And yesterday, my Wi-Fi was not so good. I have a kind of a follow-up question on this point of whether or not Granger causality, when you observe all of the nodes, whether it can actually give you the true causal graph, and maybe under what conditions this actually happens. Because I remember there was the 2014 paper, I'm not sure if you're aware of it, called Directed Information Graphs, coming out of Todd Coleman's group, which was basically talking about how I think they basically had a very strong assumption on all of the variables, which is that the joint distribution of all of the variables should be positive everywhere, strictly positive everywhere, non-zero, which amounts to having something like faithfulness, but much more. They kind of showed that under that assumption, directed information, when used appropriately, and in fact, you didn't even have to work very hard to find the appropriate conditioning set. You could just condition on everything else. So let's say you're looking at Granger causality between A and B, or directed information, or whether or not there's an edge between A and B, you could just condition on everything other than A and B, causally condition everything other than A and B, and you would be able to tell. Directed information would basically give you the answer. And I guess I basically had this question of, it sounded like through your work that there's some way of maybe refining these assumptions a little bit more and relaxing them to some extent. In part, some of the questions, some of the the point that you raised about faithfulness, I was curious about maybe how strict that assumption really is, and what does it eliminate in terms of what it assumes. And maybe if you have any other general comments in this direction of assumptions under which directed information or Granger causality actually recovers the true causal graph when you observe all the nodes.
Thank you for that question. So this assumption of faithfulness is a big assumption, and it doesn't hold in general. And when you have these stochastic processes, there are actually no real results like proving faithfulness. But if you look at the DAG-based case, what you can prove for like discrete random variables and for Gaussian random variables is that faithfulness holds. Then you're in parameterized models, right? And then you can show that faithfulness holds outside of a parameter set of measure 0. And that sounds pretty good, but it's not that good, because when you do conditional dependence tests, you may still be close. I mean, you may not be within this unfaithful set, but you may be close to it, right?
And
so
I mean, I also like the point about faithfulness holding on a parameter set that has measure 0, like or not holding on a that sounds a little bit like what's the distribution? How can you make any assumptions about the distribution of that parameter set, right? Of course you're saying that there's no deterministic relationships and so on, but that I don't know that this is always valid to even talk about but sorry, that may be a tangential point to what you're saying, so please continue.
No, I agree, it's a mathematical result, but it may not be very helpful if you're trying to from data, right? I mean, it's just a mathematical result,
right.
And it's kind of a negative result. I mean, but it kind of also, so if I mean, it also tells you that deseparation is kind of the right notion, right? Because it says that for most choices of generic choices of parameters, there's a correspondence one-to-one between deseparation and conditional independence. So that's nice, right? But then it will still give rise to very real problems when you do practical work.
That's right.
I think, I mean, it's also true, and this is true for gradient on causality, that you can, when you're learning the graph, you can just condition on everything else. But for this, you also need more assumptions, because imagine you're in a system where you have two identical processes.
Right.
Then they'll look like they don't matter for anything, just because once you exclude one of them, you still have the other one in your data, right?
That's correct.
And I think this is also a very real problem, because in very many applications you may not have identical processes. You would probably
highly correlated processes,
right? And
yes.
then you get into something where you need to do data pre-processing to get something good out, right?
That's
so
exactly right.
Of conditioning on everything else is probably also not very practical. Also, of course, if you have a large collection of processes, it's also infeasible for that reason, right? But also theoretically, it's not good, because you would need more assumptions, and one such assumption is something like independence of your noise processes. So one can form
yeah, thank you.
And I
That
think
makes
that
a lot
was
of
the
sense.
original.
And right, and to point out your example of highly correlated noise, or no, sorry, highly correlated processes. I work in the application domain of neuroscience, where this is exactly what happens, which is that you record from multiple neurons across multiple brain regions, and increasingly the complaint that we aren't recording everything to some degree, or to some approximation, you can say that that is being ameliorated by the fact that we are now able to record from more and more brain regions, essentially, and you're able to do you're able to kind of, if you think about, you're not recording from every single neuron, but you are recording hopefully from a bunch of neurons in all of the regions of interest in a particular neuroscientific task. And so the hope is that at least you are getting some kind of a sampling of all of the regions that are involved in the task. But in terms of determining which regions are actually talking to which other regions at specific points in time during that task, there is this issue of everything is highly correlated with everything else. And so conditioning on everything else is not a feasible thing. It's not clear which things you should condition on, which ones, and how, do you take subsets, which subsets, how do you do that, right? So I think that is a serious problem. Sorry, Joseph, you were saying something.
Yeah, I was just going to say that I think the original definition by Granger was to condition on all other information, right? He wasn't talking about conditioning on some specific subset. It was just saying condition on whatever you have. And
I believe, I mean, I'm thinking about the Scholarpedia article about Granger causality, where I think Granger himself had a comment there to the extent, and which I think was something along the lines of what Soren said, that you need to kind of a priori know the appropriate set of conditioning variables from, I guess, just art, or from, if you're basically from context. You should kind of know. If in the neuroscientific context, I would say if you have some anatomical priors that say region C has downstream connections to both region A and B, then when testing causality between A and B, you should probably condition on C, because C is talking to both of them.
Yeah. Yeah, I mean, it's a very interesting problem, very tough one when you have very many highly correlated processes, right?
Right.
And Praveen, I had a question about your talk, another one. I think you were talking a lot about information flows, and I've read a couple of neuroscience papers about information flows, and basically all of them talk about transfer entropy at one point, but
Mhm.
you never did. So I was just wondering why not?
So I mean, I kind of think about transfer entropy, directed information, Granger causality, all of basically be the same thing. It's
Yeah.
Granger causality is essentially the Gaussian specialization of directed information and transfer entropy. They're effectively and directed information and transfer entropy. I think people make a very big deal about instantaneous causality and whether or not to include the time point t that you're considering. I don't know if you are aware of this debate. I think that's a non-issue according to me. Like I don't know why people make such a big deal of it. I don't understand the debate around there. If you know, in I think from a practical point of view, it shouldn't be a serious debate. But so in my view, all three of these things are the same. That's what I wanted to say. And the reason that I didn't talk very much about them is there are two things that I want to mention here. The first is that I was interested always in thinking about how information about a specific stimulus or about a specific message flows within a system. And Granger causality, directed, any of these things, they don't really capture that aspect. They capture the aspect of, if I have two regions that are talking to each other, can I actually, or let's just say I have a bunch of regions that are talking to each other, I want to identify which ones are actually talking to each other directly and draw those links. So I think Granger causality is, and that's kind of why it was proposed in neuroscience as a functional connectivity measure, right? So there's a notion of anatomical connectivity, that is which neurons are actually physically connected to each other. And then there's this notion of functional connectivity, which is at a particular point in time during, while the animal is performing some kind of behavior, is neural activity actually influencing, is neural activity in region A actually influencing region B or not? And so that's this notion of functional connectivity. But I guess the thing that I was trying to do on top of this, which Granger causality and directed information transfer entropy, the things that they don't get at is, sure, maybe region A is actually talking to region B, but what is it talking about? And can you say that the information that region A is sending to region B, can you say that that information actually has to do with the stimulus, or is it perhaps just noise? Is it something that's completely independent of the stimulus? And I think that was the piece, the extra piece that we were trying to add there and build a framework for. And that's kind of where we got, I would say, we came upon the problem of, you have to deal with the idea of synergistic information, that information about a message can be spread across multiple edges and not just across any one or a couple of edges. And then how do you even start defining a notion of information flow which can capture this idea of synergy and consistently track our intuition of if I have information flowing through a system, I shouldn't lose track of it at any point in time. So how do I even define a notion of information flow that captures this? But I agree with you that I think it serves a different purpose than Granger causality does, or that transfer entropy does, and that transfer entropy would probably need to do it as a pre-processing step to what I'm proposing, in the sense that you would first need to establish that there are links, that two regions are talking, and then maybe you can ask the question of what are they talking about. So a part of what I'm doing now, or what I'm thinking about now, as well as people in the field, is how to use partial information decomposition type measures to do both of these steps simultaneously, in some sense, which is, I want not only to identify the fact that region A is talking to region B, but also the fact that they are talking about a particular message. How do I use, or how do I augment measures like directed or transfer entropy with a message? And can I use like redundancy measures from partial information decomposition to do this? Answer is yes. Are there any strong theorems about this, or like is there a theoretical framework that underlies this, to which kind of guarantees that, oh, you know what, if you do this, you will actually get the correct answer in some framework? No, that currently doesn't exist. So that's completely missing, and that's actually something that would be a very interesting thing to work on, I think.
Yeah, I mean, well, just one quick comment about what you said. Yeah, you mentioned that Granger causality is kind of a linear version of transfer entropy, which, I mean, I see how people get to that point, and it's mentioned a billion times in the literature, but still, I think Granger's original characterization was more about general predictability, right? So I think, I mean, just in my opinion, I mean, I think other people disagree. Granger causality and transfer entropy are actually exactly equivalent because like predictability and mutual information should be equivalent.
I think it's
Um,
only in the sense that the way that it's traditionally framed as, in terms of fitting an autoregressive process and then
Yeah,
looking at the error term, but I completely agree with you that yes, Granger deserves full credit for coming up with the idea that you can use the past of one process and predicting the future of another. That is the same. So I shouldn't have called it a specialization. Rather, I should call transfer entropy kind of a generalization of that idea, taking the same idea but just not thinking about linear situations alone. Yes, I completely agree with you.
yeah. And I'm also working on like really highly correlated kind of time series as well. So maybe we can discuss that later. But I think Vince had a
Sure.
quick comment before we end.
Yeah, sorry, this is kind of going back to something else. When we're talking about notions of causality, one thing that's important is like understanding the model of like what happens if you do something else, an intervention or a counterfactual. In the case of time series data, like it's well known that if you model the system as a stochastic differential equation and you know the parameters, then you know all the interventions too. Uh, like what would happen if you intervene. One question I had is, to what extent do people view the diffusion term as causal? Like how, like the drift term, which determines like how the system flows without noise. Like I think that most people, I think, view that as more important. Maybe not in economics, but yeah, I was curious to hear anyone's thoughts about, I guess, yeah, what they make of the diffusion term in an SD in terms of causality.
Yeah, I think because economists they use like these shocks to define causality essentially. I mean they think of these exogenous shocks like you have a multivariate process and then at time t you just have like this shock to the system, right? And then you see how that propagates through the system, and that's essentially the same as like total causal effects in like the causal literature. And I think in terms of the diffusion, you could think about the same, like you have your diffusion, right, which is kind of driving the system, but then at one point there's like just this, you know, atomic exogenous intervention. So you just have some impulse or something, right? And then you see how that propagates through the system. And I think that would be a reasonable way. So I don't know if people are doing that, but I think that's a reasonable way to define like total causal effects and things like that, and or to study it for diffusions, because that's what people are doing in time series. Uh, at least like yeah, I mean econometricians and physicists. That's what it, and I guess they're also doing it in diffusion models, but I'm not sure.
That makes sense to me. Like, if you have a big diffusion term, obviously it makes a big difference for interventions. But one thing, I think it was a Sokol and Hansen paper, I think it mentioned that you can kind of rotate around because the diffusion term is only known up to like the gram matrix or like the square in one dimension. Um, and I think you can just like whatever variables you can view as causal, you can just rotate around and view other ones as causal. And because it's the transpose times the matrix is still the same. Um, so like I wonder if the only thing that matters is kind of the magnitude and not kind of the source of the noise, which, if I understand correctly, is kind of arbitrary.
Um, yeah, I know the paper, but I. Mm, but I mean, if you know the system and you have the parameters, Wouldn't
Yeah, I
that
think.
yeah. Yeah, but I don't remember that. So I don't remember the paper that well. But is that not like an identification result or something like that?
Yeah, I think the idea is just that you can only identify the diffusion term up to like the idea of a square, and then you could rotate matrices so that they're square or like transpose times the matrix, or sigma transpose would be the same, and then like you can get different representations of the same like generator of the SDE.
Yeah. Yeah, and I think that's essentially the same for time series, where if you have like correlated noise terms, even if you have full observation, you're not. Essentially, you can think like, of course, like the past points to the present, right? But then in the present, there's a DAG, essentially, like there's a causal ordering also within, and that you cannot identify. So I think that's the same result you would see for time series, where you just don't, you're not able to identify essentially this ordering within time lags, and this would be the same, right? You can rotate the matrix.
Well, those noise terms aren't even in your causal graph, right? So what do you even mean by causality? Like, it's
I think they
Yeah.
are like in Soko and Hansen. I can't remember for sure.
the noise terms.
Ours is here. Do you still remember? I think she reviewed the paper.
But I think so. I think the issue is that if you look at, say, Pearl's work, in when you have like a vector of random variables, it's kind of natural that you can just like strike out one equation in your structural causal model and say that now this variable takes this value, and you call that an intervention. But then when you have stochastic processes, what is an intervention? You don't want to strike out an entire stochastic process, right? And define its entire trajectory. I don't think that's what people want to do, because then you're breaking all of the edges going into the. I think the way you want to think about interventions is something like you intervene and then you let the system run its own course. And I think that's closer to these exogenous shocks, because these atomic interventions where you just like define the entire trajectory, I don't think they correspond to the way people want to think about interventions in a dynamical system. Or maybe in some settings that's the right way to think about it, but I think in many settings you would rather think about, you push the system with this exogenous shock, then what happens. Or at least that could also be a way to think about it. I guess in economics you could also think about like increasing taxes, right? I guess that is an atomic intervention. At some point you just fix the tax level at some value.
Yeah, I feel like in general it's quite unrealistic to have that kind of atomic intervention anyway, especially if things are interacting.
Yeah.
Okay, thanks everyone. I was pleasantly impressed of everyone's talks, and I'm happy that we were able to organize this mini symposium. So yeah, I hope we all kind of keep in contact and share ideas amongst each other.
Yeah, thank you so much for organizing this.
Thank you.